12 Lab 5 Magnetic Braking with Faraday. Our goals are to collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet falling through the aluminum foil computationally via Vpython. The preview of the findings is shown below. One of the fundamental principles used is Faraday's law. When the magnetic flux or the magnetic field changes with time, the electromotive force is produced. We use the following formula, where the magnetic flux is equal to the dot product between the magnetic field and the area where the magnetic field flows through. For this lab, the following equation is used for the change in magnetic flux. The electric field produced by the change in magnetic flux follows the loop and is in the same direction as the current. Some more fundamental principles used is the magnetic force on a wire loop. When looking at the magnetic force on a loop, we have the following equation. Newton's third law states the magnitude magnetic force on the loop is equal to the magnitude of the force on the magnet by the loop and opposite in direction. Ohm's law. The current is related to the quotient of potential difference and resistance. The potential difference is the EMF produced. This is equal to the negative change in magnetic flux. As we discussed in the introduction, the physics ideas are Faraday's law, magnetic force, Newton's law, and Ohm's law. Below are more figures that relate to these ideas. We assume that the only forces acting on the magnet are the force of gravity and the force from the loop. The model assumes the magnet falls with the north pole facing downwards. The system is the falling magnet. The surroundings is aluminum foil, earth. In initial conditions is a controlled lab environment. F1 is magnetic force on a loop, and F2 is the force on a magnet by the loop. The steps of this procedure is shown below. On the left, we have a table which shows the time between the magnet first entering the aluminum foil tube and when the magnet leaves the tube. The average time interval was 0.731 seconds. The length of the tube was 0.46 meters. The width of the aluminum foil was 0.003 meters. The inner radius of the tube was 0.0165 meters, and the mass of the magnet was 0.024 kilograms. When the magnetic dipole moment was found in Lab 3 was used, the simulation predicted that the magnet would take 0.423 seconds to pass through the tube. When the magnetic dipole is increased to 2.189, the simulation predicted that the magnet would take 0.731 seconds to pass through the tube. Results suggest that the magnetic dipole moment found in Lab 3 may be inaccurate and that the 2.189 may be a more accurate value for the magnetic dipole moment. In this portion of the code, we have the physical constants, graph initialization, the creation of the tube of aluminum foil, along with the creation of the bar magnet. And on the right side, we have the initial conditions, and this is also where we are editing to create a function to calculate the magnetic field of bar magnet, along with calculating the magnetic flux. And in this portion of the code, we have the editing to calculate the gravitational force on the magnet, along with calculating the current in the ring, and finally to calculate the net force on the magnet. On the left side, we have the graph, which was generated using the code, and on the right side, we have a prediction model, which shows the direction of all the fields and the forces. Contact/friction between the magnet and the tube. Friction force would increase the time it takes for the magnet to pass through the tube. Air resistance, along with timing error when determining the magnet enters and exits the tube. And a used meter stick to measure the tube would also lead to measurement errors. Resistivity is directly proportional to resistance. Therefore, near zero resistivity equals almost zero resistance. According to Ohm's law, minimal resistance produces a huge induced current. A large current implies a large magnetic force. The magnet would drop at a slower rate because the force from the loop would be considerably smaller in magnitude than the gravitational force. Holes or cuts would interrupt the ring's continuation in the metal tube. These rings allow induced current to flow through the tube as the magnet descends. Disrupting these rings would lower the induced current. As a result, the loop's magnetic force lessens, as does its effect on the magnet. The magnet falls faster because the force on it is significantly smaller than the force of gravity.